the behavior of dielectrics and the electric field. So dielectrics are nothing but insulators, and their behavior can be modified by the application of electric field. So there are two types of dielectrics: polar dielectrics and non-polar dielectrics. Here the non-polar dielectrics are made of non-polar atoms or molecules. So in the non-polar molecules, the positive and negative charge coincide. So therefore there is no dipole moment in the absence of field. So we know that dipole moment P is equal to Q into distance between the charges. An electric dipole is two equal but opposite charges separated by a distance, and the strength of this dipole is represented by a quantity called dipole moment, which is equal to Q into d. If there are two charges, equal and opposite charges separated by a distance d, then P is equal to 1 of the charge Q into the distance between them. But in the case of non-polar dielectrics, positive and negative charge coincide. So the separation distance between the positive and negative charge is 0, and therefore the net dipole moment is 0 in the absence of electric field. So examples of non-polar dielectrics are nitrogen, oxygen, benzene, methane, etc. Now, the polar dielectrics are made of polar molecules or atoms. So, in polar molecules or atoms, the positive and the negative charges do not coincide, and therefore they are separated by a distance. So, each atom can have an individual dipole moment, but these dipoles are randomly aligned such that the net dipole moment of the system is 0. So in polar molecule, the individual dipole moments are present, but as a whole these are vectors, so they add vectorially so that the total dipole moment of the system is equal to 0 in the absence of electric field. So examples are polar molecules like water, alcohol, carbon dioxide, ammonia, HCl, etc. Now when the electric field is applied to the dielectrics, we can see that the dipole moments are induced in the dielectric. So before the application of electric field, the dipole moment is 0 in the polar as well as non-polar dielectric. So when we apply the electric field, we can see that dipole moments are formed, dipole moments are produced. That means after the application of the electric field, the dielectrics has got a dipole moment, and this phenomena is called polarization of the dielectric. So we can see this with the help of non-polar dielectrics. So when the non-polar molecule is placed in the electric field, that means suppose we have applied a positive charge over here and negative charge over here. So then we know that initially the positive negative charges of a non-polar dielectric coincide. So when the electric field is applied, there is a force acting on the charged particle, which is given by F is equal to QE. So the positive charges will experience a force along the direction of the electric field, and the negative charges will experience a force opposite to the direction of the electric field. So the positive charges move along the electric field. So the electric field is applied along this direction. Direction of electric field is known, right? Suppose we place, in order to calculate the direction, we place a positive charge. Positive charge will move along the direction of the electric field. So when this non-polar dielectric is placed, the positive charges moves along the direction of the electric field, and the negative charges move opposite to the direction of the electric field, so that there is a small separation distance d after the application of electric field. So initially, before the application, the d was 0, and after the application d is there, and there is a dipole moment q into d is there. So what happens is that all the molecules will align like this, and we have a configuration like this. So the neighboring positive and negative charges cancels, and we have a net positive charge on one side and net negative charge in the other side. പക്ഷെ ഇത് കണ്ടക്ടറിനുള്ളതുപോലെ അത്രയും ചാർജസ് ഇതിനകത്ത് ഉണ്ടാവില്ല. അതുകൊണ്ട് തന്നെ ഇവിടെ ഒരു ഇലക്ട്രിക് ഫീൽഡ് ഇൻഡ്യൂസ് ചെയ്യും, ബട്ട് ദാറ്റ് വിൽ നോട്ട് ക്യാൻസൽ വിത്ത് ദി അപ്ലൈഡ് ഇലക്ട്രിക് ഫീൽഡ്. സോ ഡ്യൂ ടു ദിസ് net positive charges will align here and net negative charges will align here, and therefore there is an induced electric field in the opposite direction, but this induced electric field will not cancel with the applied electric field, since there are enough number of free charge carriers in the dielectric as that in the conductor. So there is an electric field induced, and we can say that the dielectric is polarized. So due to this charge separation, there is a dipole moment, and initially there was no dipole moment in the dielectric, and after the application of the electric field, the dipole moment is being induced. So this phenomena is called polarization. So the induced dipole moment is proportional to the applied electric field. So as the applied electric field increases, the stretching increases, and the negative and positive charges are separated by a greater distance. So the dipole moment also increases. So when electric field increases, the dipole moment also increases, and the constant of proportionality here is called alpha, the atomic or molecular polarizability. So if the atoms in the material are uniformly polarized like this, so then the adjacent positive and negative charges cancels. So then there is a induced electric field E prime in the opposite direction. So since only the surface charges exist, the inside charges cancel. So the charges on this both sides will not cancel. This leads to an induced electric field. So the total electric field inside the dielectric is E minus E prime. So this will not be 0. In the case of conductors, E prime is having equal magnitude of that of E, since in a conductor there are plenty of charges to make the induced electric field having in equal magnitude as that of the applied electric field. But in the case of the dielectric, this will not happen. In dielectrics, E prime will be very much less than E. E prime is less than E, and therefore the net electric field inside the dielectric is not 0. Anyway, when we put a dielectric into a particular region, the electric field decreases. So now the value of the E net depends on the nature of the dielectric material. And it is found that the ratio of the applied or the external electric field to the reduced value of the electric field E net is a constant for a particular material, and this constant is called the dielectric constant K of the material. So it is the dielectric constant is the applied electric field divided by the net electric field, which is equal to applied electric field divided by E minus E prime, where E prime is the induced electric field. So initially at a region we have an electric field E. So this is air or vacuum. Then we place a dielectric material over here. Then the electric field inside the dielectric material is E net. So the ratio of these two will give the dielectric constant of the medium. So and we can see that for air or vacuum the electric field does not change. E prime is equal to 0 and K is equal to 1. And for in the case of a conductor, we know that K is equal to E divided by E prime is having same magnitude of that of E. So E by 0, which is infinity. So for conductors, dielectric constant is infinity, but for dielectrics, the dielectric constant is a finite value greater than or equal to 1. And now we discuss the dielectric strength. So we have seen that in the absence of electric field, in the case of non-polar dielectric, the positive and negative charges coincide and the separation distance between them is 0. Corresponding dipole moment is 0. So when we apply an electric field, positive charges move along the direction of the electric field and the negative charges move opposite to the direction of the electric field, but they will never escape from the atom. They are bound, but there is a separation distance and correspondingly there is a dipole moment QD. So even though there is a separation distance, they are bound together. The electron does not escape from the electrostatic field of the nucleus, and we have seen that P is equal to alpha E. So as the electric field increases, the corresponding dipole moment also increases since the separation distance also increases. So the dipole moment is proportional to the applied electric field. So D also increases, P also increases when we increase the electric field. So when the electric field is increased, the molecules of the dielectric undergo more and more stretching. So they are stretched away and the distance between them increases. But at a particular stage, when we increase the electric field further, what happens is that the stretching also increases, and so that the electrons break up from the molecule of the dielectric. That means the electron escape from the field of the nucleus. So that means the distance increases, separation distance increases, and therefore the electric field can overcome the electrostatic force of the nucleus and the electron escape. So now they are free electron. Electron is not bound to the nucleus, but this is the condition for a conductor. So electrons are free in the case of conductors only, but in the case of dielectrics, the positive and negative charges are bound. So when the electric field is increased beyond a certain limit, electric breakdown happens, or the dielectric breakdown happens, where the dielectric material is converted into a conductor. So its dielectric property is lost, and after this electric field, after the application of this electric field, the material has a property of a conductor. So the maximum electric field that a dielectric can withstand without electric breakdown is called the dielectric strength of the material. So beyond this electric field, the dielectric property is lost and the material will become a conductor, and therefore dielectric strength is the maximum electric field that can be applied to a dielectric without changing its property. കണ്ടക്ടറായി മാറിക്കഴിഞ്ഞാൽ അതിൻ്റെ പ്രോപ്പർട്ടി എൻറ്റയർലി മാറി അതൊരു കണ്ടക്ടറായി. അപ്പോൾ കണ്ടക്ടർ ആവുന്നതിന് തൊട്ട് മുമ്പ് വരെയുള്ള ഇലക്ട്രിക് ഫീൽഡ്, അതാണ് അതിൻ്റെ ഡൈലക്ട്രിക് സ്ട്രെങ്ത് എന്ന് പറയുന്നത്. സോ dielectric strength is the maximum electric field that can be applied to a dielectric without dielectric breakdown. Dielectric breakdown is the phenomena in which the dielectric is converted into a conductor. So this happens at a very high value of electric field. For the safety of the dielectrics, we can apply electric fields having value very much less than the dielectric strength. Okay, thank you.